Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asgar, and we were discussing about the synthesis and design of inorganic materials under the subject of advanced inorganic material chemistry. So far, we have discussed the high temperature synthesis method of inorganic compounds, and in last lecture we were discussing about the low temperature methods to synthesize the inorganic material compounds. Now I would like to discuss about the sol gel method, which is actually using oxyhydroxides and in colloidal chemistry. Sols and gels can be made from inorganic oxides and hydroxides by adjusting pH to form polymeric multi-cation oxyhydroxyl species at intermediate pH values. For example, the aluminium species in aqueous solution ranging from simple hydrated cations such as aluminium AlH2O63 plus in acidic solution to anionic species such as AlOH4 minus in basic solution. The reason why aluminium is regarded as an amphoteric element is that actually Al2O3 is able to dissolve in both acids and bases, but insoluble at intermediate pH values. For example, this figure actually shows some of the species that occur in the aluminium 3 plus H2O hydrogen plus and OH negative systems. Starting with hydrated aluminium 3 plus ions in acid solution and gradually adding base to increase the pH. Actually, a series of hydrolysis reactions occur. At same time, large polymeric multi-cation species may form, and this is actually the multi cation species, which actually sometimes leads to a colloidal system or a sol with nanoparticle species in the nanometer size range. These then coalesces to form a gelatinous solid of uncertain formula and structure that is often referred to as a hydrous oxide, but more correctly it is actually probably a hydrated hydroxide. With further increase in pH of the solution, this gelatinous precipitate redissolves to give complex anionic species. So, if we increase quite value of pH, then this gelatinous precipitates may redissolve to give complex anionic species. Numerous other elements of the periodic table with intermediate electronegativity also show complex aqueous solution chemistry. For example, amphoteric elements such as zinc show full range of cationic, colloidal and anionic behaviors, which is quite similar to aluminium. Slightly more electronegative elements such as zinc show the full range of cationic, colloidal and anionic behavior similar to aluminium. While if we talk about the slightly more electronegative elements show a wide range of polymeric multi-element anionic species such as vast range of complex silicate anions will be observed with silicon. Other examples which form a wide range of discrete polymeric anions are actually borates and phosphates. And we have discussed very huge details of borates in our previous lectures. Actually, the identification of these polymeric species in aqueous solution can be difficult, but in case of silicates and phosphates, they can be separated and characterized subsequently by using different chromatographic techniques. Oxides such as aluminium oxide, silicon oxide, iron oxide, zirconium oxide, and yttrium oxide are actually ideal, ideally situated as a reagent in sol gel chemistry. This is actually due to their wide ranging solution equilibria and pH dependent solubilities. So they can be used for the synthesis of complex oxides by mixing sols of different materials prior to gelation or by adding anionic solution or sometime even oxide powders to one of the sol liquids. However, this method is particularly suited to preparing thin films, fibers, and ceramic shapes. Micron thick coatings can also be used to prepare either by dip coating or spinning a sol onto a substrate, such as for the production of silica coatings on stainless steel wire mesh to increase its oxidation resistance. Some other examples of materials prepared by this route are actually discussing here. For example, synthesis of zeolites. Zeolites are actually aluminosilicate framework structures containing large interconnected voids and channels that permit ready ion exchange processes or in empty channel structure small organic molecules to enter where they can be induced to undergo various transformations or reactions. Recently related framework materials such as ALPOs, which is aluminophosphates, have been synthesized, and the methods to increase the size of the cavities in so-called MCM phases have been developed. Zeolites are more generally microporous solids, and they are synthesized by sol gel methods. It is often with final treatment under hydrothermal conditions. Hydrothermal conditions are actually the heat in high pressure water. We need to provide a stainless steel autoclave which should be lined with Teflon innerly so that we may introduce our reactants in that Teflon lined autoclave and we better to provide high temperatures, then this heat in high pressure water would known as hydrothermal conditions. A typical reaction which should be idealized is here, which is actually sodium aluminum hydroxide and Na2Si3O7 reacted with sodium hydroxide at room temperature. Then it will change into gel, and this gel should be treated hydrothermally. It means heat in high pressure water. So the temperature should increase to 175 degrees Celsius, and then it will change into zeolites. The particular zeolite that forms depend on starting composition, temperature, pressure, and also on the template that is added. The template is usually a alkyl ammonium cation around which the aluminosilicate structure crystallizes. This would also help to control the size and shape of aluminosilicate building blocks that coalesce to form a zeolite structure. So the next one is the uh, before going to preparation of alumina, I would like to give more detail of zeolite crystallization. For example, if after crystallization of the zeolite, it would be necessary to remove the template ions, and this should be done by providing heat to almost 400 degrees Celsius, where the organic material burns off, leaving the inorganic framework intact. Although these open aluminosilicate frameworks are not usually thermodynamically so stable, they are kinetically stable up to 400 degrees Celsius and are used in the range of applications at molecular sieves as well as catalyst. The next is the preparation of alumina based abrasives and films. Fine powders of doped aluminum oxide are used as abrasive grade, but to control the grade or performances, accurate control of particle size would be very important. A sol gel fabrication method is used that start from aluminium oxohydroxide ALOH, which is actually peptized or dispersed in dilute acid to give a sol, which is then mixed with the other cation containing solution of magnesium nitrate. The resulting mixtures polymerize to give a gel which is dried, crushed to give fine particles with sharp edges that caused by their fracture, and then should be fired to convert the particles into their oxides. Sol gel methods are used to fabricate aluminum oxide films and coatings. Advantages of this processing method are that the required temperatures are low and product is supposed to be more homogeneous and cheap as well. And it can also be used to coat large area substrates. In addition to this, high vacuum kit such as is needed for other film coating techniques is not needed. The resulting films are quite hard but transparent and insulate and resistance to many chemicals and abrasions and corrosion also. In a typical method, aluminium secondary butt oxide actually dissolved in isopropanol is mixed with acetyl acetone is added dropwise. Then water for stabilization and hydrolysis. The solution is reflexed at about 80 degrees Celsius for 2 hours and is then ready for coating on a substrate, which should be followed by firing to give an adherent aluminum oxide film. The films can be crystallized either by heating in nitrogen at temperatures in the range of 200 to 800 degrees Celsius for a few hours or in microwave oven for a few minutes. The next is citrate gel and Piscine process. A third family of sol gel processes, often with a combustion step to decompose the gel product, actually utilizes the carboxylic acids as a citric acid and polyhydroxy alcohols as such as ethylene glycol. In this picture we can see that actually the citric acid is a chelating agent in which carboxylate group act as the ligand to form complex with metal cations. Citric acid is quite helpful complexing agent with 3 carboxylic ligands on each acid molecule. The carboxylic acid group can also take part in esterification reactions. By the condensation with the hydroxyl group on ethylene glycol, there is much scope for varying and detailed chemistry of this reaction. Somehow other organic acid such as tartaric acid or polyacrylic acid can also be used. Other polyhydroxy alcohols ranging from small molecules such as glycerol to large polymers such as polyvinyl alcohol and polyethylene glycol can also be used. To actually facilitate decomposition of polymeric gel products, combustion synthesis aids such as urea and nitric acid may also be added to the reaction mixture. The combustion synthesis step can give highly porous foam products which could be beneficial either for subsequent ceramic processing associated with high surface area of crushed foam powders or for applications required high surface area materials. The nitric acid also acts to control pH during reaction and in particular to avoid precipitation of insoluble citrates which actually lead to loss of homogeneity during the intermediate stage of reaction or in final product. The Piscine process is actually the chemically complex and involves both acids as well as alcohols together with esterification. Whereas in citrate gel method, alcohols are not utilized and Instead, citric acid is quite simply added to metal nitrate aqueous solutions. The citrate gel method has lower organic content in gel products with less weight loss and shrinkage during firing and is often preferred for film fabrication. Many materials have been made by this process and citrate gel processes with much scope to modify the nature of final product by the attention to the actually the composition of reaction mixtures. Somehow examples may include the synthesis of superconductors for actually the use as solid oxide fuel cell cathode and lithium battery cathode. So the next process is actually the use of homogeneous single source precursors. A solid state analog of sol gel method is actually to prepare a crystalline but homogeneous single phase precursor material that should contains all the required cations in correct ratio. This precursor should not be particularly stable and on heating decomposes to give the desired product. This method actually suffers from the limitation that it is necessary to find a single source precursor that has same cation ratio as the desired product phase. Some examples of crystalline precursors which have desired properties of limited thermal stability and accurately controlled stoichiometry with cations present in the desired ratio are as follows. In A, we can see this is actually NH4FeCrO4 twice precursor to iron chromate FeCr2O4. The precursor is actually synthesized by precipitation from aqueous solution, and here we can see that this precursor is actually formed by the combination of iron 3 plus ion, chromate ion and ammonium ion. It is how decompose on heating, and the heat should be at about 1150 degrees Celsius, and then it would decompose into iron chromate FeCr2O4 and ammonia, water and oxygen. While in B step this is actually precursor to MnCr2O4. The pyridinate precursor is actually precipitated from aqueous solution and decomposed in H2, and it would also needed a pretty high temperature about 1100 degrees Celsius to further decompose into manganese chromate. In C step we can see this is actually the precursor for barium titanate BaTiO3. Barium titanyl oxalate is actually prepared by a multi-step route and decomposed by heating. While after the multi-step preparation of this barium titanyl oxalate, that we need a firing temperature equal to 650 degrees Celsius for the conversion into barium titanate BaTiO3, barium titanate oxide. The barium Ti caticulate precursors to BaTiO3. Again, a multi-step route is used, and we better to provide the same temperature for the synthesis of BaTiO3. So this would all about the different methods of sol gels to prepare different important inorganic materials. Thank you very much.